In the vacuum of space, a G-type main sequence star is an anomaly. We treat our Sun as the default setting of the cosmos, the standard unit of measurement for life, warmth, and stability. But from a purely statistical standpoint, our blindingly bright yellow host is a cosmic freak. If you were to randomly select a star from the Milky Way, the odds that it would look, burn, or behave anything like ours are mathematically microscopic. Yet, for decades, our search for a second Genesis has been entirely dictated by this singular, arrogant bias. We are hunting for a mirror in the dark. Consider the sheer volume of data cascading through the sensors of our most advanced space telescopes. We process light curves and spectral signatures, desperate to find a world nestled neatly in a very specific thermal band. We call it the habitable zone, the Goldilocks zone. Not too hot, not too cold, but the parameters of this zone have been rigidly defined by the biology of a single, isolated rock. We have built multi-billion-dollar instruments and calibrated them to ignore the vast majority of the stellar population. We are systematically filtering out the most dominant form of stellar architecture in the universe because it does not match our preconceived blueprint of what a home should look like. The real architecture of the galaxy is far more dim, far more violent, and profoundly alien. The true masters of the universe do not blaze in glorious yellow or white. They smolder. They are ancient, turbulent, and outnumber stars like our Sun by an overwhelming margin. By clinging to the familiar, we are essentially walking through a dense, roaring metropolis and assuming it is abandoned simply because we cannot find a replica of our own childhood bedroom. We are looking at the wrong light. The most mathematically probable cradle for extraterrestrial intelligence is not bathed in the comforting glow of a yellow sun, but in the relentless, deep crimson radiation of something much older and far more volatile. To understand where the true potential for life resides, we must first abandon the comforting illusions of our own solar system. We have to peer into the turbulent, blood-red shadows of the galaxy where the rules of biology and orbital mechanics are pushed to their absolute limits. If you are ready to dismantle your intuition and seek the truth in the dark, subscribe to this channel and join us on this journey. The real hunt begins when we finally stop looking at ourselves and face the terrifying reality of what actually dominates the void. For centuries, we have labored under a profound psychological delusion. We celebrate the Copernican revolution as the moment humanity finally accepted its own insignificance. We praise the historical shift from a geocentric universe to a heliocentric one, patting ourselves on the back for realizing that the Earth is not the fixed center of the celestial sphere. But in truth, we never really abandoned our arrogance. We simply transferred it. We took our biological ego, uprooted it from the soil of our planet, and projected it onto our local star. We convinced ourselves that while our planet might be just another rock, our sun must surely be the gold standard of cosmic real estate. This assumption is deeply woven into the very fabric of modern astrophysics and astrobiology. When we build radio telescopes that span entire valleys, or launch mirrors of beryllium and gold to the Lagrange points of our solar system, we program them with a specific set of prejudices. We instruct our machines to look for the familiar. We scan the darkness for Geidt-type main sequence stars. We look for spheres of plasma burning at roughly 5,500 degrees Celsius at their surface. We look for a spectral barcode identical to the one illuminating our own daylight. To understand why this intuition is mathematically and physically flawed, we must look at how we first learned to decode the light of the universe. In the early 19th century, an optical glassmaker named Joseph von Fraunhofer pointed a prism at the sun and noticed something terrifying. The spectrum of sunlight was not a continuous, perfect rainbow. It was mutilated. It was scarred by hundreds of dark, razor-thin lines. These were absorption lines, frequencies of light that were missing, swallowed by specific chemical elements in the sun's atmosphere before they could ever reach the Earth. Fraunhofer had inadvertently discovered the universal language of matter. Decades later, astronomers realized that if you applied this technique to the night sky, every star had its own unique barcode. They were not just identical pinpricks of light at varying distances, they were wildly diverse nuclear engines. At the turn of the 20th century, the brilliant minds at the Harvard College Observatory, led by women like Annie Jumpcannon, took on the monumental task of cataloging these spectral signatures. They analyzed the light of hundreds of thousands of stars, exposing them onto glass photographic plates. Through this grueling, meticulous labor, they birthed the stellar classification system we still use today, a sequence of letters that dictates the temperature, mass, and fate of every star in the cosmos. O, B, A, F, G, K, M. At the extreme left of this spectrum are the O and B class stars. These are the blue hypergiants. They are cosmic leviathans, burning at tens of thousands of degrees. They are so massive, and their gravity is so crushing, that their cores must consume hydrogen at a catastrophic rate just to maintain hydrostatic equilibrium, the delicate, violent balance between the inward pull of gravity and the outward push of nuclear fusion. Because of this ravenous consumption, these titans live fast and die young. They exist for a mere few million years before annihilating themselves in supernova, leaving behind black holes or neutron stars. A few million years is barely enough time for a planet to cool from a molten state, let alone spark the slow, agonizing process of biological evolution. So, we naturally rule out the blue giants. We move down the spectrum, past the bright white A and F class stars, until we arrive at the G class, our Sun, a yellow dwarf. It seems perfectly balanced. It has a lifespan of about 10 billion years, giving life plenty of time to claw its way out of the primordial soup. It emits a stable, steady stream of photons, bathing our planet in just enough radiation to keep water in a liquid state. This is the foundation of the habitable zone, a concept first popularized in the mid-20th century. The logic dictates that a planet must orbit at precisely the right distance from a G-type star knot, so close that its oceans boil into steam, and not so far that its atmosphere freezes into solid ice. It is a beautiful, elegant equation, and it was the absolute driving force behind our very first attempts to contact the void. In 1960, the astronomer Frank Drake initiated Project Ozma, the first modern search for extraterrestrial intelligence. He aimed an 85-foot radio dish at Green Bank, West Virginia, toward to specific targets, Tau Ceti and Epsilon Eridani. Both were chosen for one singular, overriding reason. They were roughly the same size, age, and temperature as our Sun. From that moment on, the paradigm was set. We assumed that the only way to beat the astronomical odds of life emerging from dead matter was to replicate the exact laboratory conditions of Earth. We became obsessed with finding Earth 2.0, orbiting Sun 2.0. But this obsession blinded us to a devastating statistical reality. It blinded us to the Malmquist bias. In observational astronomy, The Malmquist bias is an illusion created by the limits of our own perception. Imagine standing in the center of a vast, pitch-black continent. You look out toward the horizon and see brilliant searchlights sweeping through the dark, hundreds of miles away. You might conclude that the continent is entirely populated by giant, blinding searchlights. What you cannot see, what your eyes are physically incapable of registering, are the millions of small, flickering campfires scattered in the dark spaces between. Your data is skewed by luminosity. You are only seeing what is loud enough to scream across the void. When you look up at the night sky, almost every single star you can see with the naked eye is either a massive giant or a close, exceptionally bright star. Sirius, Vega, Rigel, Betelgeuse. They dominate our visual field. They dominate our mythology. But they are a lie. They are the statistical anomalies. The universe does not mass-produce yellow dwarfs, and it certainly does not mass-produce blue giants. The mechanics of star formation follow a brutal, asymmetrical, mathematical rule known as the initial mass function. When a molecular cloud of gas and dust collapses under its own gravity to form a stellar nursery, it does not divide its mass evenly. For every single massive O-class star that ignites, the cloud births hundreds, if not thousands, of smaller, dimmer objects. G-type stars like our Sun account for barely 7% of the stellar population in the Milky Way. Let that sink in. 93% of the galaxy looks nothing like our solar system. By restricting our search for life to yellow dwarfs, we are willfully ignoring the vast, overwhelming majority of the physical universe. We are searching a sprawling, infinite library for a single word, while ignoring trillions of pages of text simply because they are printed in a font we are not used to reading. The true nature of the galaxy is not blindingly bright. It is dark. It is cold. The dominant force of stellar evolution is not the glorious, stable burning of a yellow sun. Beneath the threshold of human vision, beyond the reach of our naked eyes, the Milky Way is swarming with ghosts. There is an ocean of objects so faint, so compact, and so incredibly dense that for most of human history, they were completely invisible to us. They do not emit the comforting yellow light of a summer afternoon. Their light is ancient, bruised, and deep infrared. These are the M-class stars, the bottom of the Harvard classification. They are the smoldering embers of the cosmos, and they are everywhere. If you were to draw a sphere around our solar system, extending out to a distance of 30 light-years, you would find a handful of sun-like stars. But within that same microscopic pocket of space, you would find hundreds of these dim, red specters. They are the true silent majority. And yet, for decades, the scientific community dismissed them entirely. The early calculations of orbital mechanics and thermodynamics suggested that any planet orbiting one of these embers would be subjected to a fate worse than hell. The habitable zone around such a faint star would have to be impossibly tight. A planet would have to huddle so close to the stellar surface just to stay warm that it would be violently gripped by the star's gravity, locking it into a perpetual, frozen nightmare. The physics seemed undeniable, but science is not a static monument. It is a grinding, relentless mechanism that eventually shreds our deepest assumptions. As our telescopes grew larger, as our spectrometers grew more sensitive, as we began to track the microscopic gravitational wobbles of these unseen stars, the data began to whisper something impossible. The mathematics of the void began to shift. We started to realize that the most hostile, terrifying environment in the galaxy might actually possess a bizarre, twisted mechanism for survival. To grasp the sheer scale of the deception we have subjected ourselves to, we must first dissect the anatomy of an M-class dwarf star. We call them red dwarfs, a term that sounds almost diminutive, benign, even harmless. But there is nothing benign about the internal mechanics of these celestial engines. They operate on a physical paradigm that is fundamentally alien to the inner workings of our own sun. Our yellow dwarf is a layered, stratified machine. It has a core where nuclear fusion rages, surrounded by a massive static, radiative zone where photons take over 100,000 years just to bounce their way outward, which is finally wrapped in a boiling convective envelope. This structure is inherently inefficient. Our sun will only ever burn the hydrogen trapped in its deepest core. When that core runs empty, the star will collapse, rebound, and die, leaving the vast majority of its outer hydrogen entirely unburned. It is an engine that inevitably chokes on its own exhaust. Red dwarfs, however, are entirely convective. From their searing core to their volatile surfaces, the plasma is in a constant, churning state of vertical circulation. Imagine a vast, boiling cauldron where the fluid at the bottom is continuously brought to the surface to cool, before plunging back down to be Because of this relentless internal mixing, a red dwarf drags every single atom of its hydrogen down into the nuclear furnace. It burns its fuel with a ruthless, agonizingly slow efficiency. The mathematical consequence of this structure is terrifying in its temporal scope. Our sun has a total lifespan of roughly 10 billion years. A typical red dwarf will continue to burn for 1 trillion to 10 trillion years. The entire universe, as we measure it, from the moment of the Big Bang to this very second, is only 13.8 billion years old. This means that in the entire history of the cosmos, not a single red dwarf has ever died. Every single one that has ever ignited is still burning today. They are the immortal sentinels of the void. If you are looking for a stable, long-term cradle for biological evolution, a place where a civilization could develop uninterrupted for billions of years without the threat of their host star swelling into a red giant and incinerating them, you do not look at a yellow sun. A yellow sun is a ticking time bomb. A red dwarf is an eternal sanctuary, and they are mathematically inescapable. To truly comprehend the scale of this mystery, we must look at the raw demographics of our local galactic neighborhood. In the late 20th century, astronomical surveys began to systematically map the stars within a 50 light-year radius of Earth. The data they returned completely shattered our heliocentric bias. They found roughly 60 G-type stars like ours. They found about 200 slightly cooler orange K-type stars, and then they counted the red dwarfs. Over 2,000 of them. They account for nearly 80% of all stars in the Milky Way galaxy. If the universe is a casino and planets are the lottery tickets for the emergence of life, the house has overwhelmingly placed its chips on red. Statistically speaking, if extraterrestrial intelligence exists, it almost certainly evolved under a crimson sky, looking up at a swollen, unmoving red sun. But how do we know they even have planets? For decades, this was the Great Barrier. Red dwarfs are so incredibly faint that observing them is like trying to study a single, dimly lit smartphone screen at the bottom of a dark ocean. We could not simply look through a lens and see a rocky sphere orbiting them. The glare of the star, even a dim one, is millions of times brighter than any light reflected by a planet. We had to rely on the shadow physics of the cosmos. We had to look for the invisible footprints left by gravity. Enter the high-accuracy radial velocity planet searcher, or HARPS, housed inside a vacuum vessel, cooled to perfectly stable temperatures near absolute zero to prevent even a micron of thermal expansion from warping its mirrors. This instrument sits attached to a 3.6-meter telescope at the La Silla Observatory in the high tundra deserts of the Chilean Andes. HARPS does not look for planets. It looks for the subtle, agonizing gravitational tug-of-war between a star and its unseen companions. When a planet orbits a star, it does not circle a stationary object. Both the planet and the star orbit a common center of mass, a barycenter, because the star is vastly more massive. This barycenter is usually located deep within the star itself, but it is slightly offset. As the planet swings around, its gravity pulls the star along with it, causing the star to wobble in a tiny, circular, microscopic orbit of its own. As the star wobbles toward Earth, the light waves it emits are compressed, shifting slightly toward the blue end of the electromagnetic spectrum. As it wobbles away, the waves are stretched, shifting toward the red. This is the Doppler effect, the exact same acoustic physics that causes a police siren to drop in pitch as it speeds past you on a dark highway, translated into the quantum mechanics of starlight. The precision required to detect this is staggering. HARPS is designed to measure changes in a star's velocity of less than 1 meter per second. That is the speed of a slow, wandering human walk. From tens of light years away, we are measuring an entire star, a sphere of plasma millions of miles wide, being pulled back and forth at the pace of a casual stroll. By mathematically mapping these microscopic spectral shifts over months and years, astronomers can calculate the exact mass and orbital period of a phantom planet. And when they pointed HARPS and its successors at the teeming swarm of red dwarfs, the data exploded. The void was screaming with planets. But radial velocity only gives us the mass. To understand the true geometry of these worlds, to know their size and density, we had to catch them in the act of crossing the abyss. We had to use the transit method. In 2009, the Kepler Space Telescope was launched into an Earth-trailing, heliocentric orbit. For 4 years, it stared unblinking at a single patch of sky in the constellation Cygnus, monitoring the brightness of over 150,000 stars simultaneously. It was essentially watching a colossal, cosmic server rack, analyzing the light output of every single node, searching for a momentary drop in bandwidth. If a planetary system happens to be aligned perfectly edging with our line of sight, the planet will periodically pass between its host star and our telescope. When it does, it blocks a microscopic fraction of the star's light. The dip in luminosity is infinitesimal. Imagine standing in New York, trying to measure the dimming of a car headlight in Los Angeles caused by a moth flying across the glass. That is the scale of a planetary transit. Kepler's photometers were so sensitive they could detect a drop in brightness of 1 part in 10,000. The data from Kepler confirmed what the radial velocity surveys had hinted at. Red dwarfs are absolutely infested with rocky, Earth-sized planets. Because these stars are small, the transit signals of their planets are deeper and much easier to detect. But the mathematics of their orbits revealed a terrifying physical reality. Because an M-dwarf burns at a fraction of the temperature of our Sun, often just a chilling 2,500 degrees Celsius at the surface, its habitable zone is compressed incredibly close to the star. If you were to place Earth in the habitable zone of a red dwarf, you would have to move it closer than the orbit of Mercury. You would have to drag it deep into the gravitational well of the star. And when you move a planetary body that close to a massive object, you trigger an inescapable mechanism of orbital mechanics, tidal friction. We experience a mild version of this on Earth. The moon's gravity pulls on our oceans, creating a bulge of water that tracks the moon's orbit. Because the Earth rotates faster than the moon orbits, the friction of this tidal bulge actually slows the Earth's rotation down by a few milliseconds every century, while pushing the moon slowly away. Now, amplify that physics by an astronomical factor. When a rocky planet is in the tight, claustrophobic, habitable zone of a red dwarf, the gravitational gradient across the planet's diameter is immense. The side of the planet facing the star experiences a significantly stronger gravitational pull than the dark side. Over millions of years, this differential force needs the solid crust and mantle of the planet, creating massive friction. This friction acts as an eternal, grinding brake on the planet's rotation. The spin slows down, the days grow longer, the braking force continues until the planet's rotational period perfectly matches its orbital period. It becomes tidally locked, like a dancer held rigidly by the wrist, forced to constantly face their terrifyingly powerful partner. The planet ceases to experience the passage of days and nights. One hemisphere is locked into an eternal, blinding day, forever staring into the swollen red eye of its host star. The other hemisphere is plunged into a permanent, freezing, abyssal night, facing outward into the cold emptiness of the galactic void. For decades, theoretical climatologists believed that a tidally locked world was an immediate death sentence for biology. The assumption was that the permanent dayside would be a scorched, uninhabitable wasteland where oceans would instantly boil into a runaway greenhouse effect. Meanwhile, the dark side would be so catastrophically cold that the very atmosphere would condense, freezing into solid sheets of nitrogen and oxygen snow, vacuuming all the air from the planet until it was left as an airless, barren rock. It was a vision of absolute physical extremes, a planet cleaved into two distinct hells. But then, we began to run the atmospheric simulations on modern supercomputers. We modeled the fluid dynamics of a thick, insulating atmosphere on a tidally locked world. We realized that nature abhors a thermal vacuum. If a planet has enough water and a dense enough atmosphere, the blistering heat of the substellar point, the exact spot where the red sun sits forever at high noon, would fuel a permanent, planetary-scale hurricane. Massive convective currents would transport the boiling heat from the day side toward the night side. High-altitude winds would roar across the twilight terminator, carrying moisture and thermal energy into the dark, preventing the atmosphere from collapsing into ice. This birthed the concept of the eyeball Earth, a planet where the dayside might be a searing desert or a boiling ocean, and the night side a permanent, fractured ice cap. But between them, at the terminator line, there exists a twilight zone, a ring of eternal dusk and dawn wrapping around the entire globe. In this narrow strip of twilight, the temperatures would remain perfectly balanced. Glaciers from the night side would melt into vast, circulating oceans. Rivers of meltwater would flow toward the day side before evaporating into the violent storm systems. It is an environment of extreme thermal engineering, an ecosystem driven by a permanent, apocalyptic weather system that keeps the razor's edge of the Terminator endlessly habitable. This is not science fiction. This is the calculated, hyper-detailed output of our best atmospheric physics, and we have already found the prime candidates. In 2016, a team of astronomers using the TRAPPIST telescope in Chile announced a discovery that redefined the field of exoplanetary science. They had been staring at a bizarrely dim, ultra-cool red dwarf in the constellation Aquarius, just 39 light-years away. A star so small it is barely larger than the planet Jupiter, and so faint that if it were placed where our sun is, noon on Earth would look like a dark, cloudy twilight. They analyzed the transit light curves. They found not one, not two, but 7 Earth-sized rocky planets tightly packed around this dying ember. The TRAPPIST-1 system is an orbital architecture so dense and so alien it defies intuition. The planets are crammed so close to the star that their orbital periods, their years, range from just 1.5 Earth days to 20 days. If you were standing on the surface of TRAPPIST-1e, a world residing squarely in the twilight zone, the red star would hang permanently fixed in the sky, huge and deeply crimson. But more terrifyingly, the other planets of the system would pass so close that they would appear as massive spheres in your sky, frequently larger than our own moon. Their surface features visible to the naked eye. You would feel the gravitational tug of these sister worlds as they constantly perturbed each other's orbits, creating transit timing variations, microscopic delays in their orbits that allowed astronomers to precisely weigh each planet from Earth. We know their masses. We know their densities. We know that several of them likely contain more liquid water than the entire Earth. Right now, the James Webb Space Telescope, with its suite of near-infrared spectrographs cooled by liquid helium to temperatures just degrees above absolute zero, is aiming its gold-coated hexagonal mirrors at TRAPPIST. It is attempting to capture the starlight filtering through the thin, theoretical atmospheres of those tidally locked worlds, searching for the molecular absorption lines of carbon dioxide, methane, and water vapor. We are finally staring directly at the most mathematically probable real estate for life in the galaxy. We have found the eternal embers. We have mapped the twilight zones. We have proven that the physical mechanics of survival are possible in the dark. And yet, as we refine the data, a deeper, much more violent reality about the nature of M-class stars is beginning to bleed through our instruments. The very mechanism that makes these stars immortal is the exact same mechanism that might render them the most efficient sterilizers in the known universe. To understand the paradox of the red dwarf, we must look deeper into the violent fluid dynamics of its architecture. The very engine that grants these stars their trillion-year immortality is also the source of an unimaginable terror. We established that an M-class star is fully convective. It is a ceaseless, churning ocean of plasma where material from the nuclear core boils to the surface, cools, and plunges back into the depths. But plasma is not just hot gas. It is a soup of electrically charged particles, protons and electrons, stripped of their atomic bonds, moving in chaotic, planetary-scale currents. When you have a massive volume of electrically charged fluid in constant, turbulent motion, you generate something unavoidable. You generate a magnetic field. In our sun, the magnetic field is somewhat regulated by its internal structure. The sun has a distinct boundary deep within its interior called the tachocline, a shear layer that separates the static, radiative inner zone from the boiling, convective outer envelope. This boundary layer acts as an anchor, organizing the magnetic field lines, keeping them relatively stable, and regulating the sun's 11-year solar cycle. Our sun is entirely capable of violence, but its architecture keeps the worst of its temper in check. Red dwarfs have no tachocline. They have no anchor, because they are fully convective from the core to the surface. Their magnetic fields are generated throughout the entire volume of the star. It is a planetary scale, unregulated magnetic dynamo. The magnetic field lines inside a red dwarf do not flow in orderly, predictable loops. They are dragged, twisted, and braided by the violently boiling plasma. They become tangled into chaotic, highly tensioned knots that punch through the surface of the star. On our Sun, when magnetic field lines break the surface, they create sunspots, dark, relatively cool regions that might cover a fraction of a percent of the solar disk. On a red dwarf, the magnetic activity is so extreme that star spots can cover up to half of the entire star's surface simultaneously. The star is literally choked by its own magnetic tension. But magnetic field lines are like physical cables. They can only be twisted so far before the tension exceeds the laws of physics. When the churning plasma forces these tangled magnetic loops too close together, they suddenly break and realign into a simpler configuration. This process is called magnetic reconnection. Imagine a steel bridge suspension cable, wound to 1,000,000 pounds of tension, suddenly snapping. Now, scale that kinetic energy up to the size of a planet. When magnetic reconnection occurs on a red dwarf, the snapped magnetic lines act like a cosmic whip, instantly accelerating trillions of tons of surrounding plasma to a significant fraction of the speed of light. The kinetic energy of the snapping field is converted directly into heat and pure, blinding radiation. This is a stellar flare, because the magnetic fields of red dwarfs are infinitely more complex and tightly wound than those of yellow stars. Their flares are proportionally devastating. We call them superflares, and we do not have to look to the deep universe to witness them. We only have to look at our absolute closest neighbor. Proxima Centauri is a red dwarf located just over 4 light-years away. It is practically in our backyard. In 2016, astronomers discovered a rocky, roughly Earth-mass planet residing perfectly within its habitable zone, Proxima b. For a brief moment, the astronomical community dared to dream that our closest galactic neighbor might harbor a twilight world, a sanctuary just a cosmic stone's throw away. Then, in May of 2019, we pointed a network of telescopes at Proxima Centauri to monitor its baseline activity. For hours, the data showed nothing but the slow, dim, steady burning of an ancient ember. But suddenly, without any warning, the star detonated. In a matter of seconds, Proxima Centauri became 14,000 times brighter in the ultraviolet spectrum. The sheer volume of energy released in that single, brief flash was staggering. If a flare of that magnitude erupted from our sun, it would permanently blind anyone looking at the sky and strip the ozone layer from our atmosphere in a matter of hours. But Earth is 93 million miles away from our sun. Earth is safe, insulated by the vast cushion of empty space. Proxima b is not safe. Remember the devastating mathematics of the habitable zone around a red dwarf. Because the star is so inherently dim, a planet must orbit incredibly close just to keep its water liquid. Proxima b is 20 times closer to its star than Earth is to the Sun. It is practically skimming the fiery surface. This introduces a terrifying application of the inverse square law of physics. The intensity of radiation is inversely proportional to the square of the distance from the source. When you have the distance to a light source, the light is not twice as bright, it is 4 times as bright. When you move 20 times closer to a star, the radiation you receive is astronomically magnified. When Proxima Centauri erupted, the planet Proxima b took the blast at point-blank range. It was bombarded by a lethal tsunami of extreme ultraviolet radiation and hard X-rays. but the light is only the first phase of the weapon. A superflare is almost always followed by a coronal mass ejection, or CME. While the flare is a flash of light, a CME is a physical object. It is a colossal cloud of radioactive, highly energized protons and electrons, billions of tons of matter, hurled outward into space at millions of miles per hour. When this invisible hurricane of high-energy particles slams into a planet positioned that closely, it initiates a brutal, mechanical process of atmospheric destruction. We call it sputtering. The process is entirely physical. The particles in the stellar wind hit the molecules in the upper atmosphere of the planet like microscopic billiard balls. The kinetic energy of the collision is so intense that it literally knocks the atmospheric gases right out of the planet's gravitational grip, spraying them into the dark vacuum of space. But the devastation is not just kinetic, it is chemical. When the extreme ultraviolet light from the initial flare hits a molecule of water vapor in the planet's atmosphere, it triggers photodissociation. The radiation is so energetic that it shatters the chemical bond holding the water together, instantly cleaving the H2O into oxygen and hydrogen. Hydrogen is the lightest element in the universe. Once severed from the heavier oxygen atom, the hydrogen is immediately swept away by the stellar wind, bleeding off into space forever. The water is irrevocably lost. The heavier oxygen is left behind, accumulating in the atmosphere. To a distant, careless observer, an atmosphere rich in oxygen might look like a biosignature, a sure sign of photosynthesizing plant life, but in the violent ecosystem of a red dwarf, a thick oxygen atmosphere is not a sign of a breathing world. It is a gravestone. It is the desiccated corpse of a dead ocean, entirely evaporated and chemically shredded by a billion years of unrelenting stellar gunfire. If Earth were placed in the orbit of Proxima b and subjected to that level of constant, violent magnetic reconnection, our entire atmosphere, every cloud, every breath of air, every drop of moisture would be entirely stripped away in a fraction of a geologic timescale. But wait, one might argue, Earth has a defense mechanism. We have a magnetic field. Deep within our planet, a molten iron core is rapidly spinning, generating a planetary geodynamo that wraps Earth in a protective, invisible magnetic shield. When the solar wind hits Earth, it strikes this magnetic barrier and is safely deflected around the planet, sliding off us like water around the bow of a ship. Surely, a tidally locked world in the twilight zone of a red dwarf could generate its own magnetic shield to deflect the flares. This is where the physical paradox tightens its grip around the throat of astrobiology. Planetary magnetic fields require a fast, energetic rotation to sustain the churning of their molten iron core. Earth rotates once every 24 hours, keeping the inner dynamo violently active. But as we have established, the brutal tidal friction of a red dwarf forces its habitable planets into a tidally locked state. Their rotation is agonizingly slow, perfectly matching their brief orbital periods. A planet that rotates only once every 10 or 20 days simply does not have the rotational kinetic energy required to sustain a powerful, planetary-wide magnetic dynamo. The shield is fundamentally broken. The very mechanism that puts the planet in the habitable zone, its extreme proximity to the star, also ensures that its primary defense mechanism against stellar radiation is inherently disabled. The planet is naked in the crosshairs of a cosmic machine gun, and the horror of this geometry extends far deeper into time than we initially realized. The final and perhaps most insurmountable, barrier to life around a red dwarf is not just what the star does today, but what the star was doing billions of years ago. We are observing these stars in their mature, main sequence phase, where they are relatively stable, save for their violent supernovas. But stars are not born stable. They are born from the chaotic, gravitational collapse of immense nebulae. When a star, like our Sun, formed, it took roughly 50 million years for the contracting cloud of gas to generate enough core pressure to ignite stable hydrogen fusion. 50 million years is a blink of an eye in cosmic terms. The Sun settled into its steady, main sequence luminosity relatively quickly, allowing the young molten Earth to cool and eventually capture the water delivered by asteroids and comets. Red dwarfs, because of their extremely low mass, have much weaker gravity. The gravitational collapse required to reach the ignition temperature for nuclear fusion is agonizingly slow. A red dwarf can take up to 1 billion years to fully contract and settle onto the main sequence. This phase is known as the pre-main sequence contraction, and it is a biological nightmare. During this first billion years, the young red dwarf is still generating immense amounts of energy purely from the friction of its own gravitational collapse. It is vastly larger and hundreds of times more luminous than it will be in its mature phase. It operates like a cosmic oven set to maximum heat, because the star is so bright during this juvenile phase. The habitable zone is pushed much further outward into the planetary system. Any water-bearing planet that formed far enough away to be safe during this initial hyperluminous billion-year phase will eventually freeze solid once the star fully finishes contracting and its light output violently drops by orders of magnitude. The habitable zone rapidly shrinks, rushing inward toward the star, leaving the distant planet stranded in a permanent, deep, frozen ice age. Conversely, consider the planets we are actually observing right now, the tightly packed worlds of TRAPPIST-1, or the rocky sphere of Proxima b. Right now, they sit squarely in the narrow, mature, habitable zone. But mathematically, to be in that zone today, they had to be in that exact same orbit billions of years ago during the star's pre-main sequence phase. For the first billion years of its existence, an eyeball Earth orbiting a red dwarf was not sitting in a comfortable twilight zone. It was sitting directly inside an astronomical incinerator. The surface temperatures would have been in the thousands of degrees. Any primordial oceans would have boiled into a thick, choking atmosphere of superheated steam, triggering a runaway greenhouse effect identical to Venus, but magnitudes worse. This steam atmosphere would then be completely exposed to the relentless, untamed ultraviolet radiation and violent CMEs of the young, violently active star. By the time the red dwarf fully calmed down, finally dimmed to its mature, immortal state, and finally allowed the habitable zone to sweep over the planet, the damage would have been irrevocable. The water would be gone. The atmosphere would be a thin, toxic ghost of heavy isotopes. The planet would be a dead, roasted husk of silicate rock, silently orbiting an eternal, smoldering ember. We are faced with a mathematical and physical impasse that is fracturing the astronomical community. The universe has engineered a trap. The most abundant stars in the cosmos, the silent majority that account for 80% of the galactic population, offer a timeline for biological evolution that is effectively infinite. They offer a stable, unchanging thermal environment that will outlast the current age of the universe 1,000 times over. They are surrounded by swarms of rocky, Earth-sized planets, existing in zones where liquid water is theoretically possible. The numbers demand that life must exist there, but the physics dictate that the cost of admission to this immortal sanctuary is survival through a billion-year gauntlet of total planetary scale sterilization. It is a paradox that pits the raw statistics of probability against the unforgiving mechanics of thermodynamics and electromagnetism. Are we looking at a galaxy teeming with resilient, deep-ground biospheres that have somehow weathered the billion-year firestorm? Or are we staring at a silent, infinite graveyard of scorched, airless rocks, endlessly circling immortal stars that murdered their own children before they even had the chance to draw their first breath? If the overwhelming majority of the universe's planetary real estate is fundamentally locked in a trillion-year death spiral of extreme radiation and magnetic violence, we are forced to reevaluate the most terrifying question ever posed by modern science, the Fermi Paradox. We look at the sheer scale of the cosmos, the hundreds of billions of galaxies, each containing hundreds of billions of stars, and we ask, where is everybody? The silence is deafening. For decades, we have conjured sociological theories to explain this absence. We assumed civilizations inevitably destroy themselves with nuclear weapons, or exhaust their resources, or retreat into digital simulations. We placed the burden of failure on the intelligence of the species, but the brutal physics of the M-class dwarf suggests a much colder, much more mechanical answer. The great filter, the hypothetical barrier that prevents matter from evolving into a spacefaring civilization, is not a sociological milestone. It is a thermodynamic wall. It is the pre-main sequence contraction phase of the red dwarf. Imagine the sheer volume of biological potential scattered across the Milky Way. Trillions of rocky worlds, rich in silicates, iron, and the basic chemical building blocks of life. They are baked in the primordial ovens. But because 80% of these worlds orbit red dwarfs, 80% of the biological potential of the galaxy is methodically, inevitably sterilized before it can ever invent the wheel, let alone a radio telescope. The universe is not empty because life is rare. The universe is empty because the universe is an astronomical slaughterhouse. The dominant mechanism of the cosmos is not the nurturing of life, but its absolute, unrelenting eradication through magnetic reconnection and atmospheric stripping. This realization casts a horrifying light on our own existence. We are not the standard, we are the statistical anomaly. We are the cosmic equivalent of a lottery winner who assumes that winning the lottery is simply how the economy works. We happened to evolve around a G-type yellow dwarf, a star massive enough to bypass the brutal billion-year contraction phase, yet stable enough to give us a 10 billion-year window of relative peace. We were granted the ultimate luxury in a hostile universe: time. Time to form oceans, time for single-celled organisms to merge, time for amphibious creatures to crawl onto land, and time for primates to look up and wonder. But this luxury is an illusion. It is a temporary, localized anomaly in a system governed by dark, infinite entropy. Suppose, for a moment, that the sheer statistical weight of the red dwarf planetary systems forces biology to find a way to survive the firestorm. If a world like Proxima b or TRAPPIST-1e is bombarded by surface-melting radiation for its first billion years, life cannot exist in the light. It must retreat. It must burrow. Astrobiologists are now heavily modeling the thermodynamics of subterranean biospheres. On a tidally locked world, completely stripped of its protective atmosphere, the surface is a desolate vacuum. But miles beneath the crust, insulated by millions of tons of solid rock, the core of the planet still generates geological heat. If there is water trapped deep within the mantle, creating subterranean, hypersaline oceans, life could theoretically spark in the absolute pitch black. It would not be driven by the gentle physics of photosynthesis. It would be driven by violent cheosynthesis, feeding off the chemical energy of hydrothermal vents, much like the extremophiles at the bottom of our own Mariana Trench. But consider the existential horror of such an evolution. If a civilization somehow evolves in the crushing dark of a subterranean ocean, they would have absolutely no concept of a sky. They would have no concept of stars, or space, or the universe itself. Their entire reality would be a claustrophobic sphere of rock and water. The very idea of an outside would be physically impossible for them to observe, measure, or even hallucinate. We are desperately scanning the galaxy for radio signals, assuming that any intelligent species would naturally build transmitters and look outward. We are waiting for a shout in the dark, but the vast majority of intelligent life in the universe might be trapped under miles of solid stone, utterly blind to the cosmos, living out their entire existence in a dark, watery tomb, unaware that there is even a universe to explore. They are prisoners of their own geology. This shifts our entire philosophical understanding of reality. We suffer from a profound temporal bias. We measure the universe by our own biological clocks, and by the relatively short lifespan of our yellow sun. We are taught that the universe is ancient, roughly 13.8 billion years old. We look at the cosmic microwave background and think we are staring at deep, finalized history. But the mathematics of stellar evolution tell a completely different story. If the dominant stars in the universe, the M-class dwarfs, live for up to 10 trillion years, then the universe is not ancient. It is practically embryonic. The time that has passed since the Big Bang represents less than 0.1% of the universe's total star-forming era. We are not living in the twilight of the cosmos. We are living in the violent, chaotic, explosive dawn. The current era of bright blue giants and stable yellow suns is a fleeting, transient phase. It is a brief, glorious firework display at the very beginning of time. Eventually, all the heavy, bright stars will exhaust their fuel. Our sun will swell into a red giant, shed its outer layers, and collapse into a cold, dead white dwarf. The O, B, A, F, and G-class stars will be entirely wiped from the cosmic inventory. When the dust clears, hundreds of billions of years from now, the universe will look nothing like it does today. It will belong entirely to the red dwarfs. They are the inheritors of the void. The cosmos will be a sea of dim, smoldering red embers burning slowly and silently in an expanding, cooling abyss. This is the true, permanent shape of reality. The universe of the deep future is a crimson dark, and this brings us to the ultimate, inescapable consequence for the human race. We look at the stars with a sense of wonder, but we must learn to look at them with a sense of cold, calculated dread. Our yellow dwarf is a ticking clock. It is slowly increasing in luminosity as the core fuses hydrogen into helium, becoming denser and burning hotter. In approximately 1 billion years long before the sun actually exhausts its fuel and dies, it will become 10% brighter. That seemingly microscopic increase in thermal output will be enough to trigger a runaway greenhouse effect on Earth. Our oceans will slowly boil into steam. The atmosphere will become a superheated pressure cooker. The Earth will be rendered entirely and permanently uninhabitable. If humanity, or whatever artificial intelligence we evolve into, survives the next billion years, we will face an absolute physical ultimatum. We cannot stay here, we must migrate. But where do we go? We cannot leap to another yellow sun. That would simply be resetting a broken clock. Why spend the unfathomable kinetic energy required to cross interstellar space only to settle around another star that will inevitably betray us? If we want a permanent home, a sanctuary where a civilization can persist, not for billions, but for trillions of years, we must conquer the very monsters we are currently terrified of. We will have to aim our generation ships toward the deep infrared light. The future of human survival depends entirely on our ability to tame the most violent, hostile environments in the known universe. We will have to arrive at a star like Proxima Centauri, recognizing that the pre-main sequence contraction is long over. The star is mature. The environment is deadly, but theoretically stable. We will not find a pristine green Earth waiting for us. We will find sterilized, airless rocks locked in a tidally enforced nightmare. To survive, we will have to engineer worlds. We will have to artificially spin entire planets to generate magnetic fields from their dead cores. We will have to construct massive, planetary-scale deflectors in orbit to shield our synthetic atmospheres from the catastrophic superflares and coronal mass ejections that still periodically lash out. We will have to huddle in the narrow twilight zones, building our arcologies in the eternal dusk. Caught forever between a boiling desert of permanent daylight and an abyss of solid ice, time will lose all physical meaning. There will be no days, no nights, no seasons, just the unmoving, swollen red eye of an immortal star hanging motionless over a manufactured horizon. Human biology, tethered to a circadian rhythm dictated by the gentle rotation of a yellow sun, will have to be fundamentally rewritten. We will have to genetically alter our own architecture to exist in a state of perpetual gloom. Our destiny is not to bask in the warm, golden light of a friendly cosmos. Our destiny, if we are to survive the brutal arithmetic of stellar thermodynamics, is to become architects of the dark. We look up at the night sky and see a tapestry woven entirely from our own illusions. We have spent centuries searching for a reflection of ourselves in the dark, absolutely convinced that the universe must share our preference for the warm, quiet stability of a yellow sun. We built our telescopes to hunt for the familiar. We calibrated our expectations to the gentle rhythm of our own planetary orbit. But the mathematics of the void do not lie. The cosmos is not built for us. It is built for the embers. When you strip away the romanticism of space exploration, you are left with a terrifying thermodynamic reality. We are the ephemeral byproduct of a temporary cosmic spring. Our entire existence, our recorded history, and our agonizing search for meaning, all of it, is playing out on a razor-thin margin of error. We were granted this brief window by a star that is ultimately destined to boil our oceans and entirely erase our planetary legacy. We are not the pinnacle of stellar evolution. We are a fleeting biological thought in a universe that is overwhelmingly dark, impossibly ancient, and profoundly indifferent. The true masters of the Milky Way do not shine in glorious white or yellow. They burn with a slow, bruising, bloody light. They enforce their dominance through magnetic violence and planetary sterilization. The trillions of red dwarfs scattered across the void are the final inheritors of time. They will still be holding their endless vigil long after the last yellow sun has collapsed into a cold, silent corpse. They are the eternal sentinels waiting in the deep future, guarding the only real estate left in a steadily cooling universe. If life does exist out there, huddled in the claustrophobic twilight zones or buried beneath the ice of tidally locked worlds, it does not look like us. It is an intelligence forged in the fires of a billion-year bombardment. It is a consciousness born in the crushing dark, shaped by the brutal physics of survival. It is intimately aware that the universe is not a nurturing garden, but a lethal furnace. Perhaps that is the inescapable answer to the silence. The Great Filter is not a test of our morality or technological restraint. It is a physical gauntlet. The silence we hear when we listen to the stars is not the silence of an empty room. It is the silence of an infinite graveyard. It is the quiet aftermath of a trillion rocky worlds that were methodically scorched bare before they could ever draw their first breath. We are entirely alone in our comfort. The Goldilocks zone as we know it is a fleeting anomaly, a gentle lie we tell ourselves to mask the crushing reality of the dark. The universe is hostile, it is endless, and it is overwhelmingly red. We have spent our entire civilization looking at the wrong stars, desperately searching for a mirror when we should have been bracing for the storm. When you walk out into the night and look up, do not search for the brightest lights. Look deep into the empty, black spaces between them. That is where the true mass of the galaxy hides. That is where the ancient fires are smoldering. And that is where the future of all things will inevitably end.